Today, we'll have two excellent lectures. The first one will be delivered by Professor Jakob Overgaard from Aarhus University, Denmark, and is entitled Quantum Crystallography in Molecular Magnetism. Jakob is Associated Professor at the Department of Chemistry of the University of Aarhus, Denmark. He's the PI of the Molecular Magnetism Research Group at Aarhus University. His research is centered on the advanced use of X-ray and neutron diffraction to contribute to understanding of molecular magnetism. He got his PhD in 2001 at Aarhus University and higher doctorate, Doctor of Science, in 2015, also at Aarhus University. I don't know whether it's formally, there is a defense or not, but with help of doctoral dissertation entitled Applications of Electron Density Studies in Molecular and Solid State Science. At the beginning of the century, he was a postdoc at the University of Sydney, Australia, then a postdoc at Aarhus University, and since 2005 to 2010, he was staff crystallographer at Aarhus University. And between 2010 and 2020, senior researcher at Aarhus University. And since 2020, he's the associate professor at this university. His high quality research is probably the best characterized by such keywords as single crystal X-ray and neutron diffraction, even powder also diffraction, molecular magnetism, experimental charge density investigations, high pressure studies. Jakob, for a couple of years, was the member of the Neutron Science Review Committee at the Oak Ridge National Laboratory, and he was getting plenty of beam times at Oak Ridge and at many others large-scale facilities. Jakob keeps continuing the best traditions of Danish crystallography, which originated from such well-known crystallographers as Finn Krep Larsen and Signe Larsen, and which have been significantly extended by Bo Iversen. Jakob and Bo are among the most important people in worldwide crystallography, as Jakob is the member of the Executive Committee and Treasurer of European Crystallographic Association, whereas Bo is also the member of the Executive Committee and Treasurer of CR. So all the firms in crystallography in Europe and worldwide go through their hands. But today we want to learn from Jakob on quantum crystallography in molecular magnetism. So Jakob, the screen is yours.
Well, thank you very much, Christoph, and of course thank you to you both for organizing this event and inviting me to give a presentation. This was a very long and flattering introduction, so thank you very much for that. I hope you can hear me and see my slides. Otherwise, I hope you will shout out. I will give a presentation today about what I call quantum crystallography in molecular magnetism. Before I get started, I will give a little background to you. Also mentioned that I did my PhD around the year of 2000, and actually at the time I was working alongside a postdoc in Aarhus whose name is Grigore Timko, and he was producing a lot of molecular metal complexes, for instance these chromium 8 rings, so that you may have seen very beautiful compounds. So this was really fascinating for me to solve all these structures, and I got interested in the topic of magnetic molecules and magnetic materials. And around the same time I read this paper on single molecule magnets, which was authored by one of the authors, the first author here, George Christou, who I'm very honored is the next speaker in this session here. And so I'm sure he will be able to correct whatever mistakes I make during my talk or answer some of the questions you may have that I cannot answer. Because my background is, of course, in diffraction and crystallography more than it is in magnetism. So what I will do today is I will actually talk about the use of diffraction methods, advanced diffraction methods, in the characterization of single molecule magnets. And this includes, as you also mentioned, Christoph, a lot of use at large facilities. And I think I hope I didn't get the beam time because I was in the review committee, but I think not. Anyway, let's get started. I have an outline which more or less consists of 3 different topics. I will briefly start talking about some of the X-ray data and just point your attention to a paper we published a couple of years ago on the use of synchrotron and the latest generation of detectors. Then I will discuss single molecule magnets, how they work, what characterize them, and how we can use diffraction method, and how we have actually used diffraction methods to address some of the important properties of these molecular magnets. So data. Data in this respect here goes back to, we want to have the best possible diffraction data. This now we are speaking X-ray single crystal diffraction data for doing charge density modeling. And this comes if you have the best possible source and the best possible detector. These are 2 vital elements. So what we did a couple of years ago, or actually more, we took 2 standard types of crystals and brought them to the Spring 8 beamline BLO2B1. This is something that was pioneered or carried by a postdoc in the group, Leonard Krause, among others. So what if we just boil it down? We made 2 findings. We looked at weak data and we looked at strong data. And in both cases, you have to be very careful not to make mistakes in the analysis or in the data reduction. So if we look first at the weak data, then if you do an experiment with various exposure times, you will see at the high resolution range, which is in the gray square here, that when you, these are the scale factor plots where you hope for a unity along the whole resolution range. And for the very weak data at high resolution, at short exposure time, you have some problems. And this turned out to be because of the almost absence of noise in the detectors. And this is something that's very difficult for the programs to handle when you have to estimate background from 0 counts. So that's just a pointer. They have to be careful when you do this, and maybe it's also specific to a particular type of software, but at least the software that we used for this study. What is more is that the strong data is also critical. Of course, you need the strong data, the low resolution data, particularly for small unit cells. You don't have so many of these, and they are often very, very strong. What we saw was that the left plot here shows as a function of transmission, so less and less as you go to the right, you have less and less attenuation. This is the extinction coefficient you can refine. You can see that the extinction is transmission proportional to the transmission, which of course it isn't, but it seems to be independent on the exposure time. And this is related to the fact that, which I will just, the explanation for this in a little while, on the next slide, that when you have on the right figure here, you see that the measured count rate in these new HPAT detectors is linear up to a certain range. So, and after that, it actually falls off because the incoming number of photons is so frequent that the individual counters are not able to measure or separate the bursts of electrons that go through this system. So there is a correction for nonlinearity, and this nonlinearity correction was not really working very well, because when you do a normal experiment, you typically make a quite wide scan, and that means that if you measure across a very strong peak, then, and if you scan across all of it, then you will only get the average flux and not the flux in a particular point. So you actually only make a correction of the average flux and not the immediate flux at a given point. What that means is that for many of the strong reflections, you have some apparent low flux. And this particular reflection is from iron and timonite, where on the right side you can see that the flux at the maximum or the peak position is more than 1.5 million. But if you see on the left side, this is a very, very narrow scan across the peak. You will find that you can see that there are some issues when you go to these very high fluxes here, where the correction actually steps in. And if you do the wide scan across the peak, you will measure something like that looks like 170,000 counts per second. So that's below, so it will not even be corrected for nonlinearity. So this is a problem, and the only reason, or the only method to solve this problem is to attenuate the beam, so you get below this high flux at the peak position, which of course is a shame, but it's still very, very high. You can also have a smaller crystal, of course. So the volume of the crystal in the beam will also change this. So these were two important observations that we made that enabled us to measure even better data than we had done before with this great new detector. And this will be important later on in this study here. Okay, so let me move on. Single molecule magnets, I will briefly just bring you slightly up to date on that topic. Single molecule magnets is a molecule. This is one definition. There are alternative definitions, but this is the one we will use here. It's a molecule that exhibits hysteresis, magnetic hysteresis below a certain blocking temperature, and it's the molecule that does it, not a bulk assembly of molecules. So returning to the manganese 12 compound, coordination compound that was described by others and also by George Christou 25 years ago, well, now almost 30 years ago. This had this hysteresis opening at 4 Kelvin, or at 4 Kelvin it collapsed, so there was no longer a hysteresis effect. This was the first time this was observed, and a very, very unique thing. But this blocking temperature was very, very low for many, many years, until a couple of years ago, where this class of compound called dysprosoceniums, they were first synthesized. People knew that they would probably be very good, but they managed to synthesize them in 2017. And now we have blocking temperatures around 60 Kelvin, which is slight variations of this actually moves it to 80 Kelvin. So we are close to liquid nitrogen and a more easy and cheap use of these compounds. So a little detail about how they work, because this is relevant for the investigations that we make. These molecules, of course, they have electronic ground states. The energy levels of the states split, or the states, they split. So according to the MS value, so if you have a spin multiplet, then the different MS values are no longer, or MS states are no longer degenerate if you have zero field splitting, which is what you have in these compounds. And now this figure here is actually stolen from George's paper from 2000, where you can see for this S equal 10 compound, this manganese 12 compound, it has an S equal 10 ground state, and the different MS states are split. So if the D value, the zero field splitting parameter, is negative, then the most magnetic states will be stabilized, and the least magnetic states will be destabilized, and you will actually end up having a bistable ground state where you can think of it as having spin up on the one side and spin down on the other side. And there will, if you populate one by putting it in an external magnetic field, when you remove the field, it will stay magnetized, the molecule, this way, even without a field to keep it this way. And the energy barrier here is, of course, important, and this is the one we are trying to address using diffraction methods. This also means that there is an anisotropy in the magnetization, so the magnetic properties are now anisotropic. This is what causes this. If you have such a molecule, you will be able to, for instance, use it for memory storage, or people are thinking about using it for quantum computing as qubits. I will not go into applications, of course, but this is intended. And then just finally, latest news from this field is a paper that was published not many weeks ago in Science by a group collaboration between people in Berkeley and people in Manchester, where they make this dimer of 2 dysprosium bridged by 3 iodines, and then you have another of these cyclopentadienyl type rings above. So when they managed to synthesize that, and they reduced it with 1 electron, so like a 1 electron reduction, putting 1 electron into this system, that electron went into a bonding orbital between the 2 dysprosium, and that generates strong magnetic exchange between the 2 dysprosium. So you have something that is extremely anisotropic. Normally you cannot get lanthanides to communicate very well. It's very weak normally, the interaction, magnetic interaction. But with this 1 electron reduction, this was successful, and it has an enormous coercive field, and that means now actually the magnetic product is getting on to fractions now of what you have in solid state magnets. So this is potentially a very, very interesting kind of material. Okay, that was just to bring you up to date on that one. I will go back to transition metal compounds, because this is what I will present here, and I will look at where this anisotropy comes from in these systems, and I will do that using 2 slides. I will look at the d orbitals and their energies and which orbitals are filled, and then I will just visualize it also in the next slide. So if you have to have anisotropy, it means you need a non-zero orbital angular momentum, and that will impart magnetic properties through the spin-orbit coupling. So if we take a look at the way I will show it here, is if you look at a cobalt-2 ion in a compressed octahedron, which has the point group D4H, what does the d orbital splitting look like? If we have just the free ion, we have 7 electrons in 5 degenerate d orbitals. So then you put it into this ligand field. They will change energies, and you will end up with a situation something like this. And now you will have an odd number of electrons in these 2 degenerate orbitals, and XZ and YZ are related just by a rotation of 45 degrees around the Z-axis. Okay, one thing is now that means we have non-zero orbital angular momentum, and secondly, this is something we may potentially be able to see in the X-ray charge density. So in a multipole model, we may actually be able to see this and even quantify this. Okay, and the visualization comes here. You see this is a metal. This is the same metal, but just the other orbital on the same metal. So you can see if you have an electron on the left side, it's here, and when it's over here, it's like this. And this, you can think of the electron moving around in a circle around the Z-axis. So you have anisotropy along the Z-axis. Okay, I hope that makes sense. Typically, we will not be able to generate a situation where these orbitals are exactly degenerate, but if they are close in energy, there will be some mixing from excited states, and that's what we call a second order effect. And this we can quantify with the zero field splitting. So I will go to the examples. First off is this what we call COMSA. Now, as this slide here showed, it's distorted cobalt in a so 4 coordinated cobalt if you distort a tetrahedron, you can get something that has D2D symmetry. And this you can control using the ligands. If you have some ligands that constrain the bite angle to the cobalt, you will be able to move very strongly away from the tetrahedral angle. And this is what's done in this compound. It was made by Van Slager's group in Stuttgart a number of years ago. And when they do dynamic susceptibility measurements, they see the outer phase of the susceptibility shows some peaks as a function of temperature and frequency. And this is the fingerprint for magnetization blocking. So this one has some kind of energy barrier towards relaxation. So if you magnetize it, there will be some barrier preventing it from just equilibrating immediately. Okay. The origin of this comes from because we compress this. And so what happens when you compress a tetrahedron? Let's see the d orbital configuration for that. So here we have the left part of this figure. This is an energy scale. So this is a idealized tetrahedron. So in the d or the states. So the d orbitals are grouped into the T2 set and the E set. E set is lower than the T2. So when you take this tetrahedron and you compress it along towards the z-axis, what happens is that the E set, they don't split very much, but the T2 set splits extremely much. So what happens is that the dxy is strongly stabilized relative to dxz and dyz, which stay degenerate here. And the fact that dxy now approaches dx squared minus y squared leads to a second order zero field splitting, because dxy and dx squared minus y squared are related by, again, a 45-degree rotation around the z-axis. Okay. And what we want to do experimentally, what we wanted to do was, can we estimate the energy barrier from the charge density? And maybe it was done in the opposite order, but anyway, let's see. I mean, if we can understand where how we can quantify this energy barrier and also the signs in the charge density, maybe we can go the opposite way and look at the charge density and derive the energy barrier. But let's see now, if we go through this figure here, maybe then we will understand. Here on the right side is the energy barrier eventually that we want to estimate. But if we start from the left here, we have a free ion. And now we are focusing on cobalt 2. This is a quartet F state. So if you put this into a tetrahedral coordination, you have a splitting into 3 terms, with the lowest is a quartet A. Then you distort this, just as I showed you the d orbital energies. Now the states will split, and we will now have a quartet B1 and a quartet B2 very close to each other. What we think is that they then correspond, and I'll discuss that more, but they should correspond to dx squared minus y squared and dxy having 1 and 2 and the other way around. Okay. And now we probably lose completely it's no longer ideal D to D, so it loses symmetry, but still then we don't give them symmetry labels, just give them numbers. So this is state 1 and state 2. Okay. Then finally, in the insert here, we can see if we apply spin-orbit coupling, it will split these 1 and 2 states into 4 different Kramer's doublets, which cannot split any further. And it's the energy difference between the 2 lowest Kramer's doublets that we are interested in, because that is actually the energy barrier for the system. Okay. And this can then be quantified. I mean, the splitting of these 2 depends on how far the difference is between 1 and 2. If there's a large difference between 1 and 2, then they will not split a lot. If there's a small difference, they will split a lot. Okay. And okay. So if we look at it from a theoretical point of view, we can calculate the configurations of these two lowest states, 1 and 2, and they are extremely pure, actually. So it turns out that 1 is essentially where you have 1 electron in xy, and you have 2 electrons in x squared minus y squared, and the excited state 2 is then you move 1 electron from x squared minus y squared to xy. So basically 1 and 2 are equal to these quartet B states. Okay, so these quartet B1 and B2, they are, since they are quartet, that means they have an S equal to 3/2, and MS is then plus minus 3/2 or plus minus 1/2. When we apply the spin-orbit coupling, they only mix same absolute values of MS. That means we will mix and split 3 plus minus 3/2 from plus minus 1/2. And again up here. So here down here, we will have some MS plus minus 3/2 coming from 1 and something coming from 2. If we do the exact calculation, we end up, this Kramer's doublet here, Kramer's doublet number 1 has 74% of the MS plus minus 3 from B1 and from 26% from B2. Okay, so this is the important number. We need somehow to correlate this, because this number we believe we can get from the d orbital populations. But how do we convert it into an energy? We do that, or we did this by calculating for a range of different compounds where you had this bite angle smaller and larger, so but you have the same kind of geometry. From those calculations, you could calculate the energy barrier or the energy splitting between the two Kramer's doublets, and you could also calculate the weight of the quartet B2 in the ground state or in the Kramer's doublet 1. And you can see this from the calculation. This is extremely linear and a very, very good fit. So if we are able now to get the weight, we can get the energy barrier. So that's what we did. And essentially, the weight is how much do we have more over 1, or how many electrons more than 1 do we have in dxy? Essentially, that's because the B2 state, the excited state, has 2 electrons in dxy. So if you mix more and more of that into the ground state, you get more and more electrons into your dxy orbital. Okay, so we did this using data we measured at Spring 8. I just wanted here because it should also have some hint of experiment. So here's a table, very good quality indicators for this compound. You have a counter ion that is causing some slight deviation, well, maybe not slight, but some deviation from the parabolic shape in the fractal dimensionality plot. But this, we think and hope, is not really causing us problems in our main molecule. So we ended up having these d orbital populations from experiment that I write here. And we can simply just type them in. It gives us these weights. Actually, it gives us 2 different, but these are details. It's related to, because dz squared is actually not fully occupied, and how do we deal with that? So we have some ideas how to do that, but let's not get lost in these details. So we have 2 different estimations of the weight of B2 in the ground state. Putting that into that formula we have here, we end up having energy barriers of between 200 and 270, and spectroscopy gives us something like 230. So at least it's surrounding the right value. So we are in the right direction. And this was very positive for us to see this value here. So at this stage, we looked, is it now ideal to just keep on compressing, because the extreme of compressing is actually a linear situation, I think. So if we look at the d orbital, idealized d orbitals for a tetrahedron, this looks like this. Then when you compress more and more from tetrahedral, and you end up having a linear system all the way to the right. But as you saw before, dxy goes down, dx squared minus y squared goes up. Eventually, they will probably meet and cross. But then what happens at some point, it will change character completely, and the orbitals will completely shuffle around. But this change over here from actually indicates, I would say here, that we have an ideal value of the angle that gives us the maximum overlap, because they are exactly degenerate here. And this is something we published last year in collaboration with Dietmar Stalge's group in Göttingen, based primarily on theoretical work and some synthesis of some compounds that was, see this figure here, the horizontal axis is this bite angle. So you have the large bite angle to the left and the small bite angle to the right. And the gray curve here actually indicates where we expect the highest energy barrier, because here these two will be exactly degenerate. Okay. So this, I think, also is an important finding I wanted to mention. So then we actually also collaborated with another group in Göttingen led by Professor Frank Meyer, and his postdoc Sandeep Gupta prepared this compound, and we used the exact same procedure. It's a very similar related compound, which I want to mention because for this one we also did polarized neutron diffraction. I hope I can talk about that. Same procedure here. Data measured at spring 8, we get some weight factors of the B2 state, and we get now energy barriers around 220 to 260, with the magnetic experiments gives us 240. So definitely we think this is a viable method. Okay, I don't know how much time I have. I hope I have 5 to 10 minutes, then I'll be very happy. I would like to discuss a polarized neutron diffraction method as well, because we did this also on this last compound. Polarized neutron diffraction, I'll probably speak a little fast now. This is something you do. You take neutrons, you have a neutron source, you have neutrons with spin up and spin down. You can polarize these, and then eventually you can flip them if you want the other direction. So when you send in a beam of neutrons on a sample, it can be either a single crystal, typically it used to be. Something very new is you can use a powder instead. But then when you send these in, you can evaluate the intensity coming out either in the Bragg peaks with spin up versus spin down, because they are not the same. They depend on the magnetization density. And so you can analyze that. This, I think also I will not get lost in this. So let me just say that the magnetization density, the Fourier transform of that is the magnetic structure factors, which along with the neutron, or the nucleus structure factors and the nuclear scattering of the neutrons is what you will get, and you need to analyze that. Eventually, you can write the magnetization as a product of the susceptibility of the individual ion times the field that this feels. Okay, so in the end, you will end up having a model. You will describe a model for each atom. You will have a susceptibility tensor. It's a symmetrical tensor. So you will be able to refine the anisotropy of the susceptibility for the magnetic ions. That's the basic outcome of this. This is not so simple, but I made it sound very easy here, which it isn't. So we did that. We did with single crystals. This is the right picture here. It's from 2018. It's a dysprosium compound. What is shown here is an ellipsoid that is showing the anisotropy is similar to a thermal ellipsoid. So it's extremely susceptible to the magnetic field along this direction and extremely not susceptible in the opposite directions, which is what you normally think of lanthanides. They are very, very anisotropic. From X-ray charge densities, we studied the same compound and found the 4F electrons, or the 4F valence density has a shape which is related to the anisotropy. And this shape, if you think of the normal vector to an like an oblate shape, not a spherical shape, but an oblate shape, then that goes along the anisotropy axis. And this is not very far from what we get from theory, or what we get from in this way with polarized neutron diffraction. So definitely we can use this method. But now I will focus on powder, because this is extremely useful. And you may think, why can you use a powder method to get anisotropic information? But if you think of it this way, you have a powder, then that means you have particles, small grains in all kinds of orientation. But if you look at one particular point on the detector, you will have only those grains that have orientations like this, or rotated around the scattering vector, Q. So you just have to average over Q, then you will actually be able to monitor this and analyze it. So this can be done, and was done. And this is something that has been pioneered by Arsen Gukasov and Yuri Kivalin from LLB. And we have just used their expertise. Firstly, we did it, you can do it on 2D. If you have a 2D detector, you can look at the summed signal of up and down, then you have an unpolarized signal. You can also look at the difference signal, which exaggerates the magnetic part, so that's the most sensitive one. What we have shown here is a model, which is to the right, simulated, and the experimental is here. Did anyone say anything? No, it's okay. I heard a sound. Good. Let me just continue then. So this is how we analyzed at first from powder. But then we recently also used it on this compound here, which I will actually not talk more about. But again, it's a cobalt too. This slide here is just to show you how reliable is the anisotropy ellipsoid, susceptibility ellipsoid that you get. So here you see the fits, the black line to that's the model, to the different signal that we measure, the blue points that we measure. This is a very good fit. So if you just rotate this around the easy axis, so you just take this cigar and you tilt it around this long cigar axis, it doesn't really change the model. So it looks like it's more or less not so sensitive to these short directions here. But if you take and rotate the cigar and point it in the other direction, the model changes significantly. So definitely we have this as the easy axis, but these hard axes are more difficult to find. Okay, so that actually is the last slide of results, because now I return to the compound that we very recently also did, the calculation of the energy barrier. And here we have the easy axis from the experiment using both powder here to the left and also single crystal polarized neutron diffraction. These two have been merged, well, not merged, but they have been co-refined. We only have one orientation of the single crystal. Normally you need three, but it seems to support very well what we get from powder PND. So this is a very anisotropic system. The anisotropy axis is along the compression z-axis, as we talked about before, and you can see here that theory and experiment agree extremely well in the direction of the easy axis here. So I will just conclude a few things and acknowledge people. I think I hope I have shown that single crystal X-ray diffraction is now at a stage where you can measure so accurately that you can and do quantum crystallography methods. You can actually extract things, quantitative numbers about the ground state configuration, and then indirectly the energy splitting. So the energy of the excited states. Also, that polarized neutron diffraction can be used to quantify the easy axis, even using a powder, which opens up doors to many, many compounds that you cannot grow multi-cubic millimeter crystals of. So I will acknowledge this work has been done with a lot of students and postdocs in Aarhus, Emil Damgaard, Lennart Krause, Emil Klan, Andreas Thiel, and Hannah Nielsen. They are former and current students who do a lot of this work. I will also acknowledge Shangda Jiang from Beijing. He pointed me in this direction of this atomic susceptibility refinement, which was done at LLB with Yuri and Arsene. And then fabulous collaborators in Göttingen, both the group of Dietmar Stalge and also the group of Frank Meyer. And then a lot of, as you said, Christoph, a lot of large facility of both X-rays and neutrons. The powder data has been measured at ILL and at LLB when before that was shut down. And we have some HIFAR data coming up in a month or two where we will try to see if it works there. And hopefully in the future, ESS will be able to take this even a step further. I will also thank funding, which has been very important, especially for the travel. Soon we can travel again, I hope. And then my final slide is, before everyone loses attention, I will just point your attention to the International Charge Density Meeting, which we have adopted this name. We call it ICDM9. It will be held in Aarhus between June 12 and 16. Website is open. Here's the link. And it will be in presence. You know, everyone, that Denmark has no restrictions anymore. So either we're all dead or it will be a great conference in June. And then I will thank you all for your attention. Thank you very much.
Thank you very much, Jakob, for this excellent lecture, which is now open for questions and comments. Please put down your questions into chat. When I was listening to your lecture, you at certain moment was also showing some dependence on squeezing, on pressure. I mean, would be great to combine this kind of studies with high pressure investigations. And have you thought about this? Have you done anything in this direction?
Yes, Christoph. We have done we have done high pressure experiments on a number of molecular magnets. Of course, as you know very well, it's difficult. You don't know what you can expect when you compress these molecules because you compress the crystal. Initially, the molecular structure doesn't change much. Eventually, it may change a little bit, but you don't know what direction. So it's we have. Let me think. I think we have not on these compounds. We haven't applied high pressure. What we did when you refer to this figure where you have the curve with the bite angle that goes from small to large or whatever, we have structures on one side and on the other side of this maximum. So what we did, we simply said we want a molecule that has this exact structure. So we made it in the computer and calculated the properties. It's not easy to get what you want. If you want to compress to reach this value, I think you have to be very, very lucky.
Yeah.
Okay, thank you very much.
We have a question in the chat by Santos Saptura. I'm sorry for wrong pronouncing. Thank you for great presentation. It's really interesting. My question is, which level of theory of the ab initio calculations that you use for ground state and d orbital purity calculations?
So we are using Orca for these. So the program Orca for the calculations. We make CAS-SCF calculations with I think isn't that called PT2? And then for the d orbital energies that when we calculate the d orbital energies, we use this ab initio ligand field theory that's implemented into this program. But it's rather heavy calculations these when you have to include the spin orbit coupling. So yeah, I don't know if that answers the question. But, it's not something I do myself a lot.
I hope so. And now we have a question from Piotr Kaszyński. Please, Piotr, you can ask the question.
Thank you, Jacob, for a very nice lecture. I enjoyed it very much, even though I'm not a crystallographer myself, I mean, by training, but I use crystallography, and I admire the technique and the level of detail one can get from the density measurements and charge measurements. So you describe polarized neutron spectroscopy, diffraction methods for getting great details on distribution of electrons and magnetic properties of metal ions. Can you do the same for organic molecules? Let's say diradicals, triradicals, or even simple radicals, just to get some details on spin delocalization or spin sign, plus or minus.
Mm-hmm. Yes, I would say yes. I mean, when you do this, when you're using polarized neutrons, you get the, I mean, you get the magnetization density. The problem is that you have to apply a magnetic field to your sample. So if you typically take a single crystal, you can grow, maybe for organic radicals it's easier. You grow a crystal, you put it in a magnetic field, and you measure when that magnetic field is on. You measure the Bragg reflections with spin up and spin down. And if you have a not strongly anisotropic, so only weakly or not at all anisotropic magnetic system, then your magnetization will align with the magnetic field that you have externally. And in that case, you will be able to actually model the spin density in like a multipole where we model the electron density. You can model the spin density from these flipping ratios. So you will have a distribution of the spin in the whole system, like we have a distribution of electrons in the whole system. So if you have this has been done for isotropic, typically it's metal ions, probably because, well, maybe the magnetic signal is stronger, or it's well, you have unpaired electrons situated on a metal site in atomic orbitals and not circulating or whatever. But in this case, in those cases, you will be able to see where you have spin up. You can even see signs of what orbitals of a metal you have spin up, and on another metal you will have spin down, and you can also see how much spin is distributed into the ligands, or onto the ligands. This has been done. Whether it has been done on purely organic systems, I'm not aware, but I don't see why. I mean, there may be reasons, but I would say yes, that's possible.
Thank you.
We have a question from Dietmar Stalke. Jakob, what do we learn from ligand design?
Yeah. Well, of course, the ligand is very, very important in this case, because you separate typically the lanthanides for themselves, and then in this case the transition metal compounds where you have stronger bonds and so on. So you want to control the d orbital splitting using the ligand field. And so if you can make ligands that bond in a strict way, you can actually control very well how the d orbitals and then the extent of orbital angular momentum in the ground state, so that the amount of anisotropy. So I think you don't learn exactly how to define or synthesize the ligands, but you can use this to see what bite angles do you want, for instance. And so if we know we want a bite angle of 77 degrees, then we have to make a ligand that provides this strictly, because it's not something that comes natural. If you have monodentate ligands, you will never get them to sit with 77 degrees between them. So as you have done, Dietmar, in your group, you have created interesting ligands that has exactly these characteristics in terms of bite angle. Of course, sometimes for these dysprosocinium, where you have a dysprosium and then you have like a sandwich compound, these sandwich compounds, they are not very stable because it's easy to enter from the side if you are like a water molecule, or so they may not be very stable. But definitely you would know that you have to make something that's quite unusual in terms of the ligands. So that they determine the properties, really.
And we have a comment from Muhammad Nadim Ashraf about the sharing the lecture slides. The whole presentation is recorded, and we will post it on the YouTube channel. So within next week, you will have an access to the video recording of this lecture. So I think that's the good way of sharing the slides as well. And we have a question from Johan Tenorio. Thanks for excellent lecture. Have you used multipolar model refinement to determine d orbital populations?
Yes. So this was done using XD. So the multipole model, the standard multipole model, really. Nothing exceptional in that case. So yeah, that was done using XD.
And Hans-Bert Birgi is asking, do you account for the localization of d electrons onto the ligands?
In where or when?
Probably when you compute, populations of the orbitals.
The CAS calculation is the active space is only the d, the 5 d orbitals with 7 electrons. So maybe, I don't know if that's the question, if that is the point, but it could be. And I have never explored it. I think perhaps someone else has explored what is the importance of including or making a larger active space when you do the calculation. I mean, the calculation gives you, it gives you these weights, I suppose. That's the important part. But really what we are using when, let's say if we talk about the energy barrier calculation, then the energy barrier is calculated from the experimental model where we get the d orbital populations, and then we use the d orbital populations to get this weight that we remember the linear scheme, which correlated the weights to the energy splitting. So if it's in these calculations of the energy splitting for a number of compounds, like to get the linear correlation, then these are all done with the same CAS 5 orbitals, 7 electrons. And that could possibly have an impact for sure. What size it is, I have not tried to find out.
And we have a question from Samair Ahmad Rater. A nice presentation. The case of dinuclear system, what will be the scenario of magnetism?
In the dinuclear system, is that the one I showed from the science paper? Isn't that the only dinuclear system we have? I think so. Dysprosium has when you talk about lanthanides, they have you can call them by their J value. So you have a in this case of dysprosium, you have a 6H15/2 state, and this is a 16-fold degenerate state. So you have typically you have MJ plus minus 15/2 for each of these, and since they're strongly magnetic, but normally they don't interact here. But in this dimer systems, you have put in an extra electron that transmit information between the two, so they actually couple ferromagnetically. So it's a very the size of the magnetic moment is large, and which I did not talk about at all, but the relaxation behavior is, some of the relaxation mechanisms are not functioning when you have this strong coupling, which is why it maintains its magnetization up to very high temperatures. I don't know if that's meant, if that's the compound.
Probably yes. I do not see any more questions. I have my questions. My question. You mentioned that nowadays you can use X-ray diffraction to measure the energy barrier.
Yeah.
And you compare it with spectroscopy. Can you comment which method is easier to be done, more accessible, or what are the positive and negative sides of two methods?
Yeah. Well, these experiments with the synchrotrons and charge density models is not something that you do very quickly. So this is a complicated experiment, very expensive in time and probably also money. So that's not. I would not say that this is something that you would use as a standard tool. So this was meant to show that you can actually extract this from, and then in this case you can measure with some infrared spectroscopy. They used, I think, in this case. That's of course in-house experiment so they did definitely much. I don't know if it's much easier. It's probably still a complicated.
How about the amount of compound you need? For successful X-ray diffraction, you actually need one good crystal.
Yeah. I am sure you need more for spectroscopy, but I don't know. I have not. We didn't do it. This was done in the original publication in Stuttgart, so I don't know.
Mm-hmm.
Sorry.
Jakob, Dietmar wants to know whether you were using multiple model in the case of dysprosium atom.
Yeah, we did. This was done using Jana because dysprosium has F electrons, so you would need higher than hexadecapole description. So you need to have L equals 6, and Jana goes to L equals 7. Mm-hmm. This is definitely even more non-standard, complicated type of experiment. Yeah, but that was also described, both using theoretical structure factors. Thanks a lot to Alessandro Giannoni for calculating those. There we could see we could actually use the multipole model to describe the electron density. So that we did with experimental data as well. Yeah.
Excellent. Are there any more comments or questions to Jakob? I do not see any anymore. So thank you very much, Jakob, for this excellent presentation and very interesting discussion.